Okay, thanks for your patience. So, chapter 2 this time in Morecroft. So we're starting to get a little bit deeper into things. So hopefully, those of you who felt that chapter 1 was a little maybe simplistic, we'll start seeing that we're starting to trickle in complexities as we go. So this whole chapter was about this sort of distinction between event-oriented thinking and this feedback systems perspective. So the event-oriented thinking is kind of the traditional way that I think people want to solve problems. The idea is we've got a goal and a current situation. We compare the situation to the goal, we get some discrepancy, and we react. And we react with a decision, and we hopefully get an action and results, which is a fix to this, which brings the situation closer to our goal. This is this being reactive means we are, involving feedback. So we're hoping that we're going to look at the real world, make a decision, which will affect the real world. So there is feedback there, where, some examples of that be, this is from the book. We've got unruly binge drinkers, put more police out there. Drug crime, put more police. Congestion, build more roads. Loss of market share, well, let's launch a new product. Decline of the fishing community, well, maybe just need more jobs for the fishing community, so we'll build a new fish factory. So each one of these is sort of a short-term feedback, a short-term fix. And the idea here is not that the feedback systems perspective that has a feedback and the event-oriented doesn't. It's that the event-oriented perspective here doesn't consider the side effects of the feedback that's implemented. So we still refer to this as kind of an open loop view. We're only thinking about the problem and the solution to the problem, and we're not thinking about how the solution itself becomes a part of the new system and what potential future problems might occur. So this is what we mean by the open loop view in this, this event-oriented model. So the idea here is that you've got a potential problem that is generated from a solution. So here, for whatever reason, you'd like to look this way, and so you push over these blocks. That's the, you're reacting to this obstruction there, not realizing that behind the scenes, that ends up setting up a domino effect, which leads to eventually your demise. So that's kind of a cartoon, what we're trying to depict as we go from event-oriented thinking to feedback systems thinking. It's not that one uses feedback and the other one doesn't. It's that the decision-making in the event-oriented perspective does not consider the feedback as part of the system used to make the decision. It just is responding to the problem by itself. So the example that they talked about here was this congestion example, where it's sort of a complicated system, or complex system actually, that we'll get into. But the idea here is, normally when we think about a problem like road construction, then there is a solution that is, well, there's pressure to reduce that congestion. And so we are going to just focus on, putting in this pressure to, we've got this pressure to reduce congestion, which hopefully will immediately, the way we respond, the problem here is that we have this road congestion, we respond to it with road construction. And from a short-term perspective, this makes a lot of sense. In the short term, if you don't have enough highway, build more highway. And in the short term, things will be spacious, and kind of reminds me, there was a Seinfeld episode where Kramer decides to donate money to sort of be a named section of road, and takes it over his own and talks about how spacious it is when you get rid of the road lines. So he just paints over the road lines, and it creates extra space, but of course it creates problems down the line. So it's kind of a similar idea here. There's a problem, and so let's just make it more spacious by adding more road construction, and that solves the problem in the short term. And if there are any future problems later, we'll deal with them as they come. That's the open loop perspective. Now, we can think a little bit through here, and this kind of simplistic feedback thinking really isn't that much of a divergence from this event-oriented perspective. This is basically the model that is being, when people say we're going to build roads, they actually do have a little feedback loop in mind, where the idea is we're going to start building roads, and the politicians will say, after a little bit of time, that'll increase highway capacity, which will decrease travel time and reduce the problem, the pressure to reduce congestion. And then we can follow that causal loop diagram around. With more pressure, there's more construction, that's the plus. With more construction, there's more highway capacity, that's the plus, but it happens after a delay because this link takes much longer than all the others. With more highway capacity, there's reduced travel time. If you have reduced travel time, you have reduced pressure to reduce congestion. So that's why that's a minus, because these two go in the opposite direction, and why that's a plus, because these two go in the same direction, and because there's only one negative, it's a balancing loop. So this is effectively still just event-oriented thinking, because it's this basic idea that we had this linear, this effectively linear causality here, where road construction ends up reducing congestion, and once the pressure to reduce congestion is sufficiently low, the feedback goes away. So it's almost like this road construction is a transient phenomena, and after we get enough roads, then we don't have to worry about this again. And so this simplistic view is effectively still event-oriented thinking. The feedback systems approach zooms out a little bit more and says, you know what, there are other variables that matter. And if you start adding in those other variables, then it gives us a different perspective on potential solutions. And so if I zoom out just a little bit, then I can think about what other things are involved in travel time. If you really do make a road so much nicer that you can get anywhere, pretty much at the speed of the vehicle, so there's really no congestion, then that's going to make an effect on discretionary trips. So in other words, it's going to become, as you decrease travel time, you increase the attractiveness of driving. That increase is why that's a minus there. As you increase the attractiveness of driving, you're going to get more trips per day. As you increase more trips per day, you get more traffic volume. And so eventually, so there really should probably be a delay somewhere in this loop here, but maybe the delay is much smaller than this delay. So that's the reason why I might throw it out. But eventually you're going to get an increase in the travel time once again. So this discretionary loop, the more attractive you make driving, this discretionary loop will make the travel time get worse and worse. So the point here, and I guess the reason probably there's a delay here and not here, is that this loop is going to be way faster than this loop. So even if you can manage to grow your highway capacity to supposedly, all things being equal, ceteris paribus, all things being equal, this would fix the problem up here. But in reality, people are going to respond in all sorts of other ways, and they're going to start using that resource in the background more than they did before. And so ultimately, you're going to lose out. You're not going to get all of the benefit that you projected you were going to get because of this discretionary loop that's down here. And if you really look at this, this is that escalation archetype. Now, we're going to start talking about a bunch of different archetypes starting in the next unit C. So we'll see a bunch of them, we'll talk about them specifically. And so I haven't really gone into great detail about what I mean by escalation and all that. Right now, I'm just trying to motivate that there are common groupings of feedback loops that we recognize. We've already seen S-shaped growth, and now we've seen escalation multiple times. And escalation is a great one I like, because it really captures this contrast between event-oriented and feedback systems. Because up here, this seems like a totally reasonable feedback loop, but you don't realize that if it's combined with another balancing loop that is in opposition to this loop. So this loop is trying to reduce travel time. This loop is effectively trying to increase travel time. So these two balancing loops fight against each other the same way your thermostat tries to bring the temperature maybe up to a set point if you're in a cold and winter months, whereas the outside tries to bring the temperature down to the outside temperature. So because they're moving in opposite directions, these two balancing loops are effectively exerting a pressure on each other, which ensures that the road construction will never end, and the trips per day will ever increase. And I think those of us who lived in big cities can probably appreciate that, or even something as simple as on a college campus. I mean, I go and give talks on other college campuses. Every campus is exactly the same. There's always construction on campus. Doesn't matter where you go. And that's because, I mean, it's complicated, but as state budgets to universities go down, tuition has to go up, or the number of students has to go up. So the way that universities solve the money problem is by scaling up, which is why all universities are getting bigger. And so there's always an increase in the number of students, but as you scale up, it creates congestion, which is why they try to find, the buildings or whatever. So, I mean, maybe I should have put the students here and the buildings there, but it's exactly the same idea. There's always construction on a campus. There's always construction in the city, because this is the typical mindset they have. But the more comfortable you make it for the people in the system, the more they'll degrade the performance of that system, causing you to have to make it more. And so you end up getting this figure eight, which this figure eight takes the odd number of links here and the odd number of links here, and odd plus odd gives you even. So you end up getting at the peripheral, effectively a reinforcing feedback loop, even though the thing in the middle pretty much stays stable. So that's what I mean by escalation. So, and that's just zooming out a little bit. We could zoom out even further than that. But does this basic picture start to make sense where, we have a simple feedback loop that, again, ceteris paribus are kind of, it's always like dangerous words, all things being equal. We can solve the problem, all things being equal. But once you introduce a solution, you've changed the system. It's almost like Heisenberg's uncertainty principle, or sort of a bastardization of that. So that, well, in reality, as you change this variable participates in other loops, and those other loops will participate right back. So any questions about this narrative? Does this make sense? How these two balancing loops can create this kind of reinforcing nature, even though each one of them is supposed to be balanced. Questions online? All right. So, like I said, in Unit C, we will talk about, we'll read a document that's actually not from the chapter, the separate document distributed on Canvas by Kim and Lannon, that goes through a number of different ones of the popular systems archetypes. These are things you probably, those of you who've taken SOS 220, it might be a review, but hopefully we can view them through a lens that has more kind of a quantitative feel to it. And we'll see behavior over time kind of coupled into that. So look out for that, looking ahead to the next unit. All right, so like I said, we can zoom out even farther and consider all of the other things that go on here. And really, if you think about it, it's not hard to come up with all sorts of reasons why making travel time, decreasing travel time will have all sorts of side effects, which may go way against your ultimate goals. So you want to reduce congestion, great, but by doing so, you're also probably going to make public transit ridership will end up being less, because more people will be willing to drive. So that's going to affect your public transit. That's going to affect the average trip length. So it's going to affect. So there's all sorts of things here that that factor into it. These are all each one of these variables that has an arrow coming into it, I would call, and this came up in some of the perusal, a so-called endogenous variable. That means that the variable is determined by other variables in the system. These variables hanging out on the side here that have to be set before you consider it, these are what we would call exogenous variables. And so these are variables that we have no idea what the process is that sets the desired travel time or sets the public transit fare. If we have a theory for how the public transit fare responds to variables in the system or other variables that aren't introduced here yet, we could build that in, and that would be something we call endogenizing the variable. So we are asserting a theory for how public transit fare responds to all these. But at the moment, we're not saying we have any idea how public transit fare is affected. So we can, if we build a simulation of this thing, we could then try different scenarios. What if public transit fare was higher? What if it were lower? And we could examine that. So I've talked about endogenous and exogenous. We're starting to get a little bit more concrete. I would say the variables that have arrows going into them are endogenous. The variables that only have arrows going out of them are exogenous. And overall, we get this complex system here of a bunch of different interacting feedback loops. And that's the feedback system's perspective. And so once we draw this, then we might get a totally different idea about what's the right way to move forward. Maybe we want interventions down here and not interventions up here. Maybe simply building more roads goes against our long-term goals. And so then we might say, well, maybe we can, if we don't reduce or increase the roads, are there things we can do down here? Maybe we just make public transit cheaper. Maybe we try to make it more attractive to take the bus. You know, maybe we give incentives for carpooling, and so on and so forth. And so that would mean adding links in down here and maybe leaving this alone. Okay. All right, so so any questions about, again, this congestion narrative? Hopefully this resonates with you. A lot of you sure have driven in urban areas where you've experienced this sort of thing, or just gotten frustrated about construction. And this is, I guess, comes from a real case study where Morecroft came in London and was sort of analyzing with other policymakers different perspectives. So this is a simplified version of some of the models that they built there to investigate different approaches that they could go in to try to not just throw more roads at the problem. Yeah.
Okay, so I see the systems and I see the dynamics, but I don't see the sustainability. So what we're looking at is really historical systems understandings of the way things work. Basically, don't have an answer for sustainable systems.
Right. So the sustainability comes into play. So again, this is the name of this title. This course is called System Dynamics and Sustainability. And so the idea here is that once we build this, the next step is to build that simulation model allows us to do behavior over time. And then we can start doing scenario planning where we start assessing sustainability metrics in the long run.
Right. So in this case, we probably as a solution
that
which would reduce congestion as well as the problem.
Right. I mean, you're asserting a hypothesis there that we could then investigate through the model by either playing with these exogenous variables or adding in additional links here that would be a model following from that hypothesis. Absolutely. And then we could then study, we would have to choose, what are we calling a sustainable? Maybe sustainability means continued economic activity without an significant increase in highway capacity over the next 100 years or something like that. And so we could simulate a number of different hypothetical 100-year forecasts with maybe different public transit fares, different things here, and we could see under which ones of them does highway capacity necessarily have to balloon, and under which one of them does it actually stay kind of stable. And so far we've really just talked about strategic thinking, scenario planning, but then adding in that sustainability piece is then what metrics are we going to use to evaluate those scenarios that would come out of the behavior over times that will be generated from. Yeah.
So is like the second
Well, I would say that it's about sort of drawing boundaries. And so I would say that if we back up to say that if we assert as policymakers that this is enough to make decisions with, that this is our conceptual model of how urban traffic works, then that is sort of an event-oriented perspective or simplistic feedback thinking, where we're really sort of just saying that the only lever that we have to play with is road construction. And so what we're trying to say here is that we have to be careful when we draw our boundaries, because in reality, a probably more realistic system that we need to be thinking about when we make decisions includes not only the immediate effects of our intervention, but also the additional feedback loops that are already in place, that if we manage to change a variable somewhere, those other feedback loops will kick in. And so, and they will then, it's like feedback is a tricky thing. Like, it's actually really hard to study what we refer to as the innate immune system, which involves also, like, when you cut yourself, how your body responds to being cut. And the reason it's hard to study that is that under normal situations, you're not bleeding, right? So you don't actually observe your body responding to being cut until you actually make the cut. And so it's a similar thing here. If you didn't know, like, you don't realize that there are these additional feedbacks that are just waiting to be triggered. And if you don't model them explicitly, then your world is going to seem like this. Like, I might think if I get there are people who can't clot and all that sort of thing. It's like if I get a paper cut without thinking about the whole system, I could die, right? And some people can if they don't have, the right additional feedbacks. But in reality, if we think about human physiology, they actually do have responses to that. And so, we need to sort of the hidden feedbacks, especially if they're balancing, are often cryptic, and they don't come out until we actually make the intervention. And if it's a really costly intervention like road construction, then we may just be stuck with it. So that's why we're just sort of saying that we need to make sure there's not other feedbacks, especially balancing feedbacks, that under status quo are not operating. So under the status quo, people are just taking a certain number of trips per day and hitting a certain traffic volume. So we don't see this until we make it that we reduce the travel time. And then suddenly, whoa, the trips per day increased. Where'd that come from? Well, it turns out that human psychology responds to changes in traffic, to travel time. So that's what we're kind of saying here, is that we need to try to be careful about drawing our boundaries. And before you go in and introduce an intervention, then you have to back up and say, are there other variables that are related to the variables that are in my loop? And let me put those out there and make sure there's no other feedbacks that might work against me. Any other questions about this example or these contrasts? Again, this is sort of SOS 220 type stuff, but it's good to just get us all on the same level playing field. All right, so there was this popular book in the 90s that in some cases you read this and you think, it just makes sense, right? Like, why is this even a thing? But it actually took people time to convince people to think this way. And so one of those books, The Fifth Discipline, talked about this systems thinking perspective as a way to get people to step back and think about the consequences of their actions. And they referred to this as a shift of mind. And again, today we kind of take it for granted, hopefully, that it makes sense to kind of think a little bit more circumspect, I guess. So think about sort of everything here, but people had to argue for that. And so that's kind of this. What is this shift of mind? And this is just kind of what I just said here. It's that we've got a problem, we've got a solution, and we've got additional feedback loops that we have to consider. And if you only focus on your problem, goal, situation, discrepancy, and your solution, that simple feedback loop, all things being equal, if none of this gray stuff happens, you will solve the problem. But in reality, as you start tweaking variables here, these hidden feedbacks, especially the balancing ones, balancing feedback loops they come to equilibrium, kind of like a population comes to equilibrium at carrying capacity. Like, it just sits there. Like, if you just look at a fish population sitting at carrying capacity, you don't see any reproduction going on. It's only after you take a bunch of fish out, you start seeing them bounce back. So if you just look at a fish population, you might think they don't ever reproduce, they just live forever. But in reality, you take a bunch of fish out and you can study how quickly they bounce back, and then you can start understanding how quickly they actually reproduce. They just didn't have the opportunity to reproduce when they're sitting at carrying capacity. So the same idea here is that we have to make sure that we're not overlooking other feedbacks that will kick in the instant our solution to the problem kicks in. And that's this idea behind feedback systems thinking. So it's not just thinking about adding feedbacks, but it's thinking about systems of feedbacks and making sure we include all of them. And that's really the shift of mind. that we're talking about. So any questions over that general sort of perspective about the difference between event-oriented open loop perspectives and the feedback systems perspective? It's really about kind of having a myopic perspective where you don't look beyond your solution, or having kind of this circumspect perspective where you consider all of these feedbacks. Okay, all right. Okay, so this was just review over what we've been talking about, but this was Morecroft's take on causal loop diagrams. So I just point out he doesn't talk about partial derivatives or anything like that, but he does point out things like under link polarity, the plus means that if the cause increases, the effect increases above what it would have otherwise been. So again, it's relative to a no change baseline. And so it's this idea that if you didn't perturb the system, you'd have a certain amount of eaten and a certain amount of hunger. And if you increase the hunger a little bit, how much does the amount eaten change relative to what it was, and vice versa. And so that's kind of all that's being seen there. So does anybody have, there were some questions that came up in the muddiest points where people are still kind of figuring out how to assign these pluses and minuses. I can tell you, more than one person is not quite, 100% comfortable on these right now. So are there any questions anybody wanted to share about any of this, or do people feel like they're at least heading in the right direction with these link polarities? Does it make sense what we mean by setting a plus here and a minus here? Questions online? Okay. Yeah. So the question was, when we construct these pluses and minuses, do we always tell the story about increasing? Like, do we always say, if the cause increases, what does the effect do? And so I would say, no, you can also say it the other way. That's one of the reasons why some people prefer not to use plus and minus, but same and opposite. So where S is the same as plus and O is the same as minus. So when your knowledge, sometimes it's just conceptually easier to think about the decrease narrative. Like, if I decreased hunger, what would happen to my amount eaten? But I think the reason why Morecroft just uses the heuristic here of increase only is the idea here of, if you had an increase in hunger, then here you can kind of use the link polarity as the response to an increase. And so the thought here is, if I had an increase in hunger, I would get an increase in amount eaten. So that's why it's the plus. If I had an increase in amount eaten, I'd have a decrease in hunger, and that's why they use the minus. So if that works better for you, always use increase. And that's totally fine. In fact, that's actually the nice thing about always using increase is you don't get stuck in the trap of accidentally following a change too far. Like, I could say, if I increase the amount eaten, I decrease my hunger. Now, I'm tempted to then say, if I decrease my hunger, then I'll decrease my amount eaten. But when I say that, my brain hears decrease, and it's tempting to put a minus there. I have to remember that the decrease was in response to the decrease here. So one of the nice things about always using increase is it forces you to not ever accidentally flip your perturbation around and forget that you did it. So I can say, if I increase my amount eaten, I will decrease my hunger minus, reset. If I increase my hunger, I will increase my amount eaten plus. And so that's the advantage of using the increase. But as long as you're careful, you can do whatever makes most sense to you. Any questions? That was a great question. Any other questions about that? Question online. So the pluses and minuses, in this case, are positive and negative changes. And so we can think of the plus as representing that there will be a positive change to amount eaten if there is a positive change to hunger. The minus here means there will be a negative change to hunger if there is a positive change to amount eaten. So if you prefer, you can think of the pluses and minuses as the response to a positive change of the cause. That's one way to think of it. Alternatively, again, same or opposite. If you think plus is same, then that just means that the two sides of the arrow do the same thing, and minus O, the two sides of the link do the opposite thing. Any other questions about that? How do CLDs help us identify loops but don't need to have loops? So there was I mentioned in the chapter that these are called causal loop diagrams, but they don't always have loops. They just help us identify loops. And the idea here is that finding feedback loops is super important. Sometimes it's hard to find that they're there until we draw the diagram. So it might be that I draw this thing, and like if I were to go to the next slide, well, like here, like if I were to go to this slide here, I have 3 variables, but these 3 variables, and I'll talk about what this is about here, but these 3 variables do not participate in a loop. This is still a causal loop diagram. And if you just describe the system to me, I might not know if there's a feedback loop or not. But after I actually draw variable A, variable B, variable C, and all the links, then I look at this and I say, well, this is how they're all causally related, but there are no loops here. So it's still a causal loop diagram because I used it to find a loop, but I ended up not finding a loop. So it's still a CLD, but it doesn't have a loop. So CLDs don't have to have loops. They're used to find loops, because once we find a loop, that's where the really interesting dynamics happen. Without a loop, everything's kind of just a copy of everything that's sort of causally upstream of it. But with a loop, that's where you get things that sort of start reshaping in interesting ways. So hopefully that answers the question. That CLDs identify loops, but they don't need to have loops, even though there's a loop in the name. So are there any questions about that? Does that make sense? Causal loop diagrams do not need to have loops, but they help us find the loops. Okay. Questions online to all those? Okay. Right, so the other thing we have to be really careful about is that the links in causal loop diagrams are not purely correlational. They are causal. So we can have a common cause for 2 effects. We can have that something changes here, and very quickly something changes in another part of the system, and a little bit later something changes in another part of the system. That's what this delay is about. Now, that's going to create a correlation between effect 1 and effect 2. And on top of that, it's going to look like effect 1 happens first, and then effect 2 happens in a predictable way. So we will be tempted to, if you just were describing the system to us, if we forgot about this common cause, to draw this link, where because there is a negative correlation between effect 1 and effect 2, it just so happens that whatever effect 1 goes up, effect 2 will go down a little bit later. So it will look like effect 1 might be causing effect 2. But if we don't have a mechanism that we are theorizing is responsible for that cause, then we can't assert that link there. We really need a causal link, or at least a theory of cause. And simply that 2 things happen together, or one thing happens after the other, is you can't immediately assume causation. So there's 2 fallacies that are named by their kind of Latin name, cum hoc ergo propter hoc, or post hoc ergo propter hoc. The first fallacy with this, therefore because of this. The second one after this, therefore because of this. So you have to be careful you're not committing either of those when drawing a link, that you really need to sort of say, what is the causal mechanism that I'm theorizing exists between effect 1 and effect 2? Because if you don't have that mechanism, you're not going to end up being able to simulate it. So that's kind of the big deal. And so we want to really capture our theorized causal connections. And so if there's a common cause, we need to include that common cause. We don't want to just have these described correlations. So does that make sense? We're going to avoid these 2 fallacies. This is both after which and with which. So both this line could be drawn for either of these fallacies. but that would be incorrect because there could just be a common cause causing both of them. Okay, so causal loop diagrams are causal bookmarking, not correlational, or bookkeeping, not correlational bookkeeping. Okay, good. Tips. So these are tips from Sturman. So Sturman wrote the expensive and giant tome Business Dynamics, which is kind of the major for like when system dynamics modeling is talked about in business school and B school, then they typically use this kind of big, thick business dynamics book. And what Sturman talks about are these are the things that he thinks go into a good causal loop diagram. And these are decent tips to go by. Use curved lines, because again, causal loop diagrams are about finding feedback loops. And so if you use curved lines, then those loops pop off the page because they turn into ovals. And so similarly, when you do have loops, then you want to try to have them follow circular or oval paths. And that gives me an opportunity to jump down to the last one here. If you do notice a loop, you can feel free, and you probably should, redraw your existing diagram to try to make that loop pop a little bit more. And there are actually tools that I'm not going to show you, but they're in there in Vensim, and I can point them out if you want, that where Vensim will attempt, or Insight Maker will attempt to do this for you. But a lot of times, when a computer starts redrawing your diagrams for you, it's not quite like DALL-E or anything like that. It ends up being kind of ugly. So it's best to sort of use those not on a really giant model, unless it's a really giant model you were given and it's just terrible, it's like a spider web, then you can give it a shot. But if you've got a pretty nice looking diagram on its own, you tell the computer to redraw it, it's probably going to go in the wrong direction. So, but you should be free to redraw. And this is the big reason why computer tools are particularly good at CLD instead of hand drawing. Minimize crossed lines, again, because those create the appearance of loops when they're not really there. Again, causal diagrams are finding loops. And minimize chart junk. And so Sturman's big message here is, again, because you want your eye to find the loops, you don't put boxes around variables because it's extra lines that are going to confuse your eye. You should just have naked variables and curved lines, and that's it. That should all be on, maybe delay symbols, but that's all that should be on your CLD. So any questions about these general guidelines? Hopefully, especially in the second part of your homework where you're drawing that giant, or maybe the first part of your homework where you're drawing that big, those two kidney shaped, you'll sort of get the feel for creating this continuity in the flow. Okay. And then Morecroft's additional tips are about how to choose those variables. And he goes on at some length there where each variable should be a noun or a noun phrase. You can add adjectives as a noun phrase, but try to avoid things that have action or things that have direction. So you want to try to put as much of the action or direction into the links, into the causal links, and keep the sort of the nouns as sanitized as possible. And when you're choosing these words for your variables, you want to give it some impression of measurability. And we'll have some examples of that coming up next here, where you want to try to sort of say, even if there isn't an obvious measure, there is a theoretical measure you could imagine creating as some index that, what I like to actually tell people, sortability. Is there a way that I could quantifiably sort these things, even if I can't quite put a number on them? Like, I can't say there's exactly 3 units of happiness, but if I could say that this person is happier than this person is happier than this person, and so on, then maybe happiness would be something that I could use as a variable, because in theory, I could increase my happiness, and I could decrease my happiness. So he uses measurability, I use kind of sortability, but it's the same idea. And we'll see examples of that here in a second. So any questions about these 3.5-ish rules, I guess, guidelines? Questions online? Check the anonymous question pool. Okay, so let's practice that. So here's a bunch of words I threw up here on, I vomited up here on the board. Things like marketing budget, increase in cost, attitude, deliver performance, delivery lead time, temperature, increasing prices, morale, water, experienced staff, flow of water, and happiness. And so of all of these, then we want to sort of figure out which ones do we think are good variables and which ones are bad variables. So can anybody point out what they think might be either a good or a bad variable? Yeah. So and that makes it a good or a bad. That makes it a bad variable. It's an increase in cost because there's, it seems like cost should somehow be enough. And so increase in cost is it's adding direction. So, and I think I would probably agree with that. I would put this in the bad column. You could say, well, how does something affect the increases in cost? But then it seems like a layer of indirection. So let's just put that increase into the link. Any other thoughts? What are good or bad variables that you see? Yeah. Yeah, I like that too. So we're saying flow of water might be a good one because it's very clear. We know that there's no ambiguity on what about the water we're talking about. Flow could be positive or negative. We could imagine sorting, high flows and low flows. So yeah, I think flow of water is a good one. And those online, if you want to put something in the chat, I'm also happy to monitor that. Any others? Well, let me see if anybody else. Yeah. Yeah, good point. So attitude is a hard one, right? Because it's kind of ambiguous. There's probably better choices. You might know what you mean by attitude, but in any writing, it's never about the writer, it's about the reader. And so attitude, we could probably be clear about what we mean by attitude. So that could have raised red flags if there's going to be ambiguity to someone. Because what you're thinking of attitude in one direction, somebody else might be thinking of attitude in a different direction, might totally change the causal loop polarities. Somebody mentioned increasing prices here online. They said that is a verb, so this is a negative here. So online, we're saying that because there's this direction word, increasing prices, it sounds like this is probably a bad choice because we could just say prices, because it's adding that as how can something increasing prices or decrease? It's weird to say, how do you decrease increasing prices? So rather than playing this double negatives game, just push it all into the link. Any other thoughts? Any other obviously good or bad variables? See online, anybody? Or let's see, how did I do? So this is, I'm not saying this is 100% right or wrong, but this is the way I would group them. These are all ones that I like a lot for good variables here. They seem very clear to me. We already talked about flow of water. Delivery lead time, I like that because it's very measurable. I know it means, how much time is it going to take for me to get the sofa that I ordered or whatever. Temperature, morale is a little bit of a funny one because it's kind of a little bit lofty or whatever, but still it's not, if you think about it, it's not very ambiguous, whereas attitude was very ambiguous. And I already talked about happiness. Experienced staff, I would like to point that one out because it's slicing staff in a way that is very useful. So we could just say the number of staff, but somehow that's probably not going to be the salient feature of the system that's going to drive the dynamics. We probably need to know how much experienced staff we need versus new staff or something like that. So that's the reason why that particular, you might look at that and say, doesn't that seem like a directional word? But it's not, because it's partitioning the staff in a way, because experienced staff probably affect the system different than new staff. Similarly, marketing budget, that also, you think, well, that adjective, is that too much? But here, if we just said budget, it'd be too generic. So marketing budget tells us, okay, it's the amount of money we're putting into marketing. So that makes a lot of sense to me. Now, these over here, probably bad. I say, there's probably ways that you could justify using these in special cases. But for the most part, they're a little too ambiguous to me or too directional. We talked about attitude already. Delivery performance, that's one that tricks a lot of people up. I would not use delivery performance as a variable because I don't know what you're measuring. So delivery lead time I like because I know that you're measuring lead time, but there's a bunch of different things about performance, and there could be negative things as well. Like could be like amount of things that delivered people broke, that sort of thing. That could also be a measure of delivery performance. So it's not quite sure, what you're measuring there. And water, something like water level might make sense. If the context is clear, then maybe water is enough, but usually we think of water more as an adjective or more like, we like flow of water, water level, but water doesn't, like, I can't sort water. I can't say, I couldn't say there's more water in this bucket than this one, but then I could probably be more specific and say water level or amount of water. So water by itself, is it a noun? Is it an adjective? I don't really know. So yeah. So any questions or comments about this? Again, I'm not saying these are 100% right, but if you put a gun to my head, so to speak, this is how I would categorize them, and I would feel relatively good about these categorizations. But there could be some arguments, especially about these ones in the probably column. So any comments or questions or concerns about that? It's pretty clear at least why even if you might have put something in another bin, you at least buy why I put them in these bins. Okay. All right, good. Questions online? Okay. All right, so going along the lines with measurability or sortability, a nice trick, and it's ends up being useful once we get into actually building the sims, is that as you pick your variables, also try to pick units. And if you can't come up with a unit, it's probably not measurable or sortable. So like, for example, marketing budget, well, that's easy. That's in terms of, in this case, pounds per month, dollars per month. So I have a number, and that number exists on a number line. And if it exists on a number line, it's measurable and sortable. I know what a larger marketing budget and a smaller marketing budget is. Same thing with sales. Things like industry reputation, that's a tricky one, right? Because there's no standardized unit of reputation. On the other hand, it's sortable. We can say that this company has a good reputation, this company has a bad reputation, and this one's, it's in between. You'd probably prefer it over one or the other. So you could imagine that somebody could come up with an index of reputation, and it would be based on a bunch of things that could be measurable, and they could end up, scaling it from 0 to 1. And then, you could assign those numbers to different companies and sort them by that. So because it is possible for me to imagine a way for a company or an industry to have a better reputation or a worse reputation, I would say it's still measurable, even though I don't quite know what the measure is. So it's a little tricky, but I hope you can see that industry reputation is qualitatively different than water, So I don't know how to sort water, but I can imagine sorting companies by reputation. And if you say, I still know what you mean, I could probably say, what are your feelings for Apple, Google, and Microsoft? And it might be that across the whole room here, we have different opinions about those three companies, but each one of you probably could come up with a ranking of those by reputation. And then so we could imagine aggregating over that, and then that might give us, a sorting over for this American population. This is how those three generally rank on average. Similarly, things like bidding power, that's a weird one, right? So we have to operationalize what it means to have bidding power. And so what does it mean for a company to have bidding power? Well, that means that they win a lot of their bids. So we look at all the bids that are out there for companies that are bidding, and we look at how many people win those bids, or how many companies win those bids, and the fraction of total bids is the bidding power. So we can imagine a unit for that. So some questions about that. What we mean by setting up units, and these abstract units, even though they don't quite exist, they exist kind of in theory, in fantasy. You could, in theory, come up with some index that would allow you to sort them. Questions online? So measurability and sortability. This kind of relates to all of that. Okay. All right, I'll let that sit for a second and stew. And then, so at the beginning of the class, when the question was, all right, saw the dynamics and the systems, where's the sustainability? And so kind of give a preview of this, and kind of like, where do we go next? And so, and this idea is in the dynamics. Like once we actually can build dynamical models, we have a way of connecting more directly to sustainability questions. And so, what I mean by dynamics. And so, we are going to see, as we especially go to unit C and look at the archetypes, and then in unit D, where we start actually simulating in BinSim and InsightMaker, a lot of these BOTs or BOTGs, behavior over time graphs. And we've seen a lot of them popularized in the pandemic. So this was from a while back. This was the reproduction rate, and doesn't matter what that means. We'll actually build SIR models, and we'll talk about reproduction rates and basic reproduction numbers and all that. But this basically is a measure of how infectious, in this case, COVID was, and it's plotted over time. So this is like March of, I'm not sure which year in this particular plot. It looks like they've kind of got overlapped, but but it's over time. They're watching that there was a peak in infectiousness and it came down. And you notice that as this BOT plot is up here, they put little markers, like here's where shelter started, here's where there was the gradual reopening of society, here's where shelter ended. And by looking at these graphs of real data, then it suggests theories of dynamics. It suggests that what happened with shelter, what happened with reopening, and so on. So we're looking at the dynamics, and we're analyzing features of dynamical curves to try to come up with possible explanations for what's happening. And so this was a paper from Public Health Journal using BOTGs to spur systems thinking among public health practitioners. And so in this case, they're plotting here the annual per capita cigarette consumption from 1900 to looks like 2000. And you see it's got this kind of peak and then down here, and they've sort of pointed out different things that happened, like it rose and then the Great Depression hit and then it fell. And then after the Great Depression, it started rising again, and then this is World War II and so on. And so looking at the dynamics over time and interleaving them with exogenous events. So the thought is here that there is some process which is driving the adoption of cigarette smoking. And that process, there's a fundamental process which explains maybe this general curve, but then these deviations from the curve are perturbations that are from exogenous variables being changed, like the Great Depression. That wasn't something that's built into the sort of salient model of this World War II, et cetera, et cetera. And so so that's kind of like, behavior over time graphs. They add a richness where they start allowing us to think about events and their long-term consequences or their short-term consequences. So what are the background pressures and what are the short-term responses? That's what these BOTG graphs help us with. And so in this paper where they're calling on people, this isn't that old of a paper actually, it's 2018 in Public Health. And so they're saying here that public health practitioners can use BOT graphs to spur discussion and systems thinking around complex challenges. They talk here that by drawing them and annotating events and systemic forces that are likely to influence them, it allows them to create a more holistic understanding of key factors that contribute to a trend. And I think they also talk about how it helps bring participants together. So this is a different sort of paper here where they talked about doing group model building. So they talk about these behavior over time graphs, help them share ideas and experience across disparate groups that might have different things to bring to the table about a particular discussion. And so that's kind of the idea that we're heading at here, is that by looking at dynamics, we can start thinking about long-term effects and how they relate to these short-term relationships, which we can observe. If I back out and stop thinking about public health and all that, we can think about simpler examples of that. So this is an example that Morecroft brings up a lot in the book, which is the slow to respond shower. And if we think about the fundamental feedback system in the shower, we've got, in this case, he's saying, assume the flow of cold water is constant, and the person in the shower is just adjusting the hot water. So they have a desired temperature. There's an actual temperature. Based on the gap between that, they adjust the hot water. A little bit later, the actual water changes, and this thing goes around. And so if we think about it, there's the common sense model here is that there's, this is water temperature, and this flat line is your desired temperature. You imagine that it's going to start cold, and over time, slowly, it'll eventually rise and then hit the desired temperature. Now, ideally, it would do that very quickly, right? So it would just rise very quickly up, and it would hit that desired temperature. But what we find out is in reality, it probably goes well above the desired temperature, well below, and oscillates until it eventually, way down far out, settles down there. And systems theorists, the mathematical systems theorists, actually have names for these three different modes of behavior. So we refer to this thing here as overdamped, critically damped, and underdamped. And I'm not going to quiz you on those three terms, but I bring that up because the point is that this loop, under different parameter configurations, can produce all three outcomes. And so these seem like qualitatively different outcomes, but they're really just quantitatively different outcomes of the single feedback loop. And so all of these can come out of this simple feedback loop with a delay. So if there's a short delay, you'll get maybe one output. If there's a really long delay, you'll get a different output. So you can imagine if this delay is really long, you're probably going to be in this underdamped mode. And you can actually even get farther things where these oscillations ring and almost seem to never die out. But in most physical systems, they'll eventually die out. So this is kind of an example of that. Siri is talking to me, I think, because I touched my headphone. Okay. All right. So the idea here is that this model here all can come out of this simple water example here. So if we're thinking about building, let's say, a shower in a hotel, for example, we might imagine that these are all of the outcomes that we could get out, because this is what goes on inside a single shower inside a single hotel room. And so when we look at this, we think, well, as long as we maybe adjust the delay, then we can maybe make sure all of our hotel occupants get close to the ideal. But we have to ask ourselves, from the feedback systems approach, are we including all of the variables? And in reality, in something like a hotel, then there might be a shared hot water source. So there's another room out there, and they've got exactly the same shower, but they're competing for the same hot water. And this archetype, where there's a balancing loop, another balancing loop, and they're coupled by a reinforcing loop. And this is reinforcing because the idea is that if you ask for more hot water on one shower, you'll reduce the hot water on the other. And then likewise, if you ask for more hot water at the other shower, you'll decrease hot water on the other one. So this overall is going to mean that as you ask for more hot water on one, you're gonna get this sort of growth in the requests for hot water. And that's this reinforcing loop, which is coupling these two balancing loops. And this, when you combine these three things together, you don't get the simple model here, the balancing with delay. You get something that we'll learn about. It's called accidental adversaries. And so this is a common coupling when these three things come together, and they have a qualitatively different output. And that output looks more like this, where the dark line is shower head 1, the blue line is shower head 2. And like you can see, it's got oscillations, which look a little bit like the oscillations that you can get in the balancing with delay, but it's also got growth. So it combines balancing with delay and escalation. So remember escalation. If I could go back to this link here, if these two balancing loops didn't have the reinforcing in between it, if there was just one single flow of hot water in between them, this would be escalation. But the additional dynamics from these two flow of hot waters competing against each other is what causes this escalation to not just grow, but also have these interesting oscillations here too. So the envelope here grows continuously, while inside the envelope there are these oscillations. So each person in the shower thinks that things are getting hotter and colder and hotter and colder, and then if you zoom out, it's getting the peak heat gets higher and the peak cold gets lower over time. Now, eventually, this can't go on forever. You end up just maxing out. All the hot water goes to one shower, and then all the hot water goes to the other shower, and so on and so forth. And so, in reality, what's going to happen is that the human who's controlling the shower is going to be smarter than the feedback system. That's been a simple feedback system that's been modeled here, and the dynamics of how the human controls the system will end up resolving this conflict. But if we just model the human as just responding immediately to the temperature gap, rather than adding their own delays and how they're controlling it, then we'd expect to get something potentially that looks like this. And this is the typical outcome from a so-called accidental adversaries archetype. And so this behavior over time is not immediately obvious when we just look at this causal loop diagram. But if we simulate this causal loop diagram, then we can actually start saying, what are the real consequences of this in the long run? And this clearly is not a sustainable outcome. And so that's kind of a picture of where we're going with that. Now, thinking about showers doesn't seem like a very useful application, but it's a nice model system, as they talk about in the chapter, for thinking about other similar problems like this Harley-Davidson problem that they kind of talked about in the book that Morecroft was involved with. And so the idea here is that Harley-Davidson has two major ways it makes its income. They build motorcycles. They also sell parts to people who service motorcycles. Orders come in to both divisions, and the central Harley-Davidson business center here decides on where to invest within the company. So they will then send money and resources to parts, or money and resources to the motorcycle side. And depending on their decisions, then you can get different lead times, let's say, on your parts or on your motorcycles. And so I think when Morecroft was a consultant for Harley-Davidson or a similar company, they were trying to understand these kind of boom and bust cycles that they were getting, where their customers would sometimes get parts immediately, but other times have to wait for weeks to get their parts. And it was almost unpredictable whether the parts would come quickly or take a long amount of time. And when he mapped out what was going on here, he found that the two units of the company shared the same capacity management area. And what was happening is, just like those showers competing for hot water, there was so much limited capacity here that they could only effectively be a parts company or a motorcycle company at one time. And so if they wanted, just like the hotel, if you want people all across the whole floor to get hot water, you maybe need to make sure you have a lot of hot water available, or a separate hot water reservoir for every room, like a hot water tank for every room, or again, a way to get water to every room very quickly. Likewise here, if you need to make sure that your company can really support being two companies, and if this is happening, then you might need to expand your capacity in order to ensure that there's always enough resources to do both things at the same time. And so effectively, this is exactly the showers, the example, up here that we've talked about here. It's just using a different currency. It's not water anymore. It's money that's going to either parts or motorcycles. And so clearly there are a lot of differences between dueling showers and dueling, motorcycle subunits, but the fundamentals are so similar that if you need to just simply explain boom and bust cycles, then you have to start saying, are there capacity limitations that are causing different parts of the same system to share a limited resource? And if they are, it's that limitation that's probably generating those boom and bust cycles. And so that comes by thinking dynamically about the long-term consequences of things that we can draw in the short term, these relationships. So that's kind of where we're going with that. So any questions about that general idea? As you stew over that, I don't want to keep you too much longer, just reminders. There's this applying systems archetypes, a reading on Canvas. This is not due until next week sometime. And upcoming assignments, don't forget that assignment B2 from last week is due on Sunday. There's another Muddiest Point on Sunday. And there's this homework, if you're interested in looking ahead, it's already available, but it will be formally released in the next lecture. So we'll talk about that thing. So with that, let's give you an attendance exercise, and again, happy to take happy to take questions afterwards, or you can get out of here. So let me put the link in the chat. And the question I have for the day here is, what is the name of, and if you don't remember this, again, it's fine, but what is the name of the new archetype we discussed today that combined two balancing loops with a reinforcing loop? So again, we've been talking about escalation for a while, and now we added in a new archetype that had two words in its name, and it had a balancing loop and a balancing loop, just like escalation, but a reinforcing loop tying them together. And what was the name of that archetype? And again, we'll talk about a lot of archetypes as we start Unit C and the Kim and Lannon article. So it's not expecting you to immediately digest all these archetypes. That's coming, but I just want you to be prepared for that. And with that, that's all I got for you today. So if you've got any questions, feel free to ask. Otherwise, we'll see you on Thursday. Any questions online? All right, in that case, I will go ahead and close the room. See everybody Thursday.